Okay, good. So we just did the FOM method. What we're going to do now is going to be very similar to this, but it's going to be the GMRES, which I keep misspelling and miswriting in my notes. So GMRES. So when we did the one-dimensional projection, we saw the minimized residual error. This is the generalized minimal residual error. And in this case, we're going to take, it's going to be our K space, that is our search space, is going to be the Krylov space, and then our orthogonality space, L, is going to be A times K. So we're going to be in this situation. Okay, so the setup is going to be K is equal to Km, which remember is a span of R naught all the way up to A, M minus 1 R naught, like this. And then the orthogonality space L is going to be equal to A times K, or since K is equal to Km, it's going to be equal to A times Km. Now, there are various ways that we can interpret this, but remember, as always, what we're doing is we want to find some delta in Km, and we want Xm to be equal to X naught plus delta, and we want the residual B minus AXM, which, as we have seen multiple times, we can write as R minus A delta. We want this to be orthogonal to L. I'm not going to use fancy L since I'm not using it up there. We want that to be orthogonal to the space L, which is equal to A times Km. Okay, now as we have discussed before, really what we're looking here is A delta is going to be the orthogonal projection of R naught onto this space right here. That is sort of the mathematics that's driving this. But at the level of formulas, you might want to copy this down. At the level of formulas, what we want is we want R naught minus A Vm Ym. We want this to be orthogonal to the space L. And remember, L is equal to A times K. Okay, so what does it mean for this to be orthogonal to A times K? Well, it means if you take any vector in the space A times K and then you do the dot product here, you're going to get 0. So similar to how we have written these equations before, these orthogonality equations as matrix vector equations, we can write this as A Vm transpose times R naught minus A Vm Ym is equal to 0. Okay, now why does this do the thing that we want it to do? Well, if you think about the matrix A times Vm, Vm contains a basis, its columns are a basis for the Krylov space Km. So if you do A times Vm, the columns of this matrix, that is the column space of this matrix, that will be a basis for the space L, which is just A times K. And so now, if this matrix vector product is equal to 0, what we're saying is that for every vector in a basis for a VK, dotted with this is going to be equal to 0, and therefore every vector in the space dotted with this vector is going to be equal to 0. Now we can rewrite this. We can rewrite this in the following way as A Vm transpose A Vm Ym is equal to A Vm transpose R naught. And now we're going to use the fact that the Arnoldi relationships between A and Vm are such that A times Vm is equal to Vm plus 1 times H bar. And so now, this left-hand side is going to be A times Vm is Vm plus 1 times Hm bar. So when you take the transpose, you're going to have Hm bar transpose V M plus 1 transpose. And then again here, AVM is VM plus 1 times HM bar, and then times Y. Okay, well, what about the right-hand side? Well, the right-hand side, the transpose is on the wrong thing here. Transpose should be here. AVM transpose, well, we're going to get, this is equal to, again, VM plus 1 HM bar. So when we do the transpose, we're going to have HM bar V M plus 1 transpose R naught. Okay, now what's happening over here? That's going to be the M plus 1 by M plus 1 identity matrix. So the left-hand side is now HM bar transpose HM bar YM is equal to what's happening on the right-hand side. We've got VM plus 1 transpose times R naught. Well, again, the first row of VM plus 1 transpose is going to be V1, which is simply R naught divided by its magnitude. Okay, so when you do this matrix vector product, you're going to get beta E1, and you still have HM transpose. There should be the bar there. All of the H's here should have the bar. Okay, so now the equation R naught minus AVM YM, where YM is in RM, this is orthogonal to L, is equivalent to this equation here. So in other words, the YM that satisfies this equation is the YM that satisfies this condition, and the YM that satisfies this equation is the YM that satisfies this condition down here. Okay, but one thing that we can look at is the following. So I'm going to erase everything from up here. The equation that we're solving. So for the FOM method, the small problem that we solved was HMYM is equal to beta 1 E1. We get something very similar here. The small problem that we're going to be solving is HM bar transpose HM YM is equal to HM bar transpose beta E1. So this is the problem that we want to solve. Okay, this is the small problem that we solve. Okay, so both FOM and the GMRES method replaces the big problem, AX equals B, with a small problem. Now, in principle, we could just solve this problem right here. Okay, there's various ways that we might come up with good strategies for solving this problem. In principle, we can solve this problem right here. The issue, though, is that this matrix is worse numerically than just HM. In particular, what I mean is that it's condition number squares. Okay, so the condition number is the ratio of the biggest eigenvalue to the smallest eigenvalue, and you want a small condition number. So here, the condition number squares, which means there are potential problems with solving this. Problems that you don't have with just HM. So what we're going to do is recognize that the form of this problem right here is really, there's a least squared problem going on. So let me just remind you, if you want to solve an equation like mx is equal to b, for this equation to have a solution, b by definition has to be in the column space of m. And if it's not, the best thing that you can do is try to minimize mx minus b, the norm of mx minus b, in the 2 norm. Now, as we've seen before, the solution here is going to be the x such that mx minus b is orthogonal to the column space of m. In other words, if b is the projection onto the column space of m, the solution is going to be is going to be the x that satisfies mx is equal to the projection on the column space of m. This is stuff you've seen before, so I'm not going to talk a whole lot about it now. But this is the problem we want to solve. If we can't solve this, this is our backup plan, and our backup plan will also get us a solution if this has a solution. So this is the backup plan, but this equation right here is the same. This minimization equation is the same as m transpose times mx minus b is equal to 0, because we're saying mx minus b is orthogonal to the columns of m. That's what this equation here says. And then if we want to, we can write this as m transpose m x equals m transpose b. And these are called the normal equations. There's always a solution to this equation, even when there's not a solution to this equation. So we always have a solution to this equation. The solution to this equation is the same as the vector x that minimizes this, and a vector x that minimizes this is going to be a solution to this equation as well. Okay, so why am I mentioning this? Well, if we look up here, I can notice I have an HM transpose here and an HM transpose here. So this is a normal. These are the normal equations for a certain system. In particular, h bar ym is equal to beta e1. So in other words, I'm saying hm bar ym is playing the role of mx, and beta e1 is playing the role of b. So the solution to this equation here is the same as this minimization problem, where again m is equal to hm bar, x is equal to ym, and b is equal to this. So instead, the problem that we solve is to minimize for y in Rn. Let me write it in the direction that the book has it. Beta E1 minus Hm bar Yn. Okay, and because of the computations that we went through, this is going to be the same as minimizing delta in Km of R naught minus A delta. Okay, and remember, this is simply by the standard computations that we've done a million times. It seems like this is going to be the minimum, again, over delta in Km of B minus A xm, where xm is equal to our initial guess x naught plus delta. Okay, so in other words, we are minimizing the residual. So that's why it has this name, minimizing the residual. What is the algorithm? So foolishly, before I made this video, I erased everything that I had here before from the FOM algorithm. So the initialization steps that I had here for the FOM algorithm are going to be the exact same initialization steps that we have over here. Everything here is going to be the same. The only thing that's different is step 12. And step 12, what we're going to do, instead of solving HMYM is equal to beta E1, we are going to solve the least squares problem to minimize what we have up here. Beta E1 minus HM bar YN. And so in terms of practical applications, when we implement this algorithm, the FOM and the GMREs are going to be very similar, except at this step for the GMRES, we are going to do a minimization here. We're going to solve a least squares problem here. Now, for the homework that's going to be due, or for the homework that is due next Monday, we're just going to use the standard NumPy or SciPy least squares solver here. And I'll talk a little bit about that during the lab. But we're also going to look at methods that allow us to sort of, so both for this method and the GMRES method, it'd be great if the Hessenberg matrix was actually upper triangular. So we're going to see methods that we can actually transform this step by step into an upper triangular matrix. That is going to allow us to do these solves, both this one and for the FOM, a little bit better. But that's sort of like, that is a level of, so right now I want to keep it at a certain level of abstraction. We just solved this system right here. Once we have a good feeling for that, which is going to be hopefully after the homework, then maybe for the project we'll implement what's going to happen if we want to have a more a better method for solving these systems right here. But right now I'm going to keep it at this level of abstraction, though in the lectures and the labs I'm going to talk about how we can practically or more practically kind of compute the solutions to some of these systems of equations where the matrix is a small upper Hessenberg matrix. Anyways, okay, that's it. This is the GMRES algorithm. It is just very similar to the FOM algorithm, but we're looking at L is equal to AK rather than L being equal to